Okay, so welcome everyone to our final day of our mini course. And well, as it happened before, I realized yesterday that I could have mentioned something else um, related where we were discussing purity and also thermostates. And of course, we were doing that for an harmonic oscillator. So that was, yeah, that you can use the same notions of purity that we have in traditional quantum mechanics. And I think it's a very natural. So since we were all, it's all about introducing the algebraic framework, and then it's a very natural question to say, well, what does it even mean to talk about pure state in the algebraic framework? And yeah, I didn't. I mean, this. I'm just mentioning this because I'm not going to discuss this at length. But there is a very natural generalization because in finite dimensional systems, you can show that the condition of purity, for example, using rho squared as a measure of that, is in fact equivalent to the statement that if you can't write a density matrix as a convex linear combination of two other density matrices, and in that statement can be generalized for our functionals. So in algebraic framework, we can define a pure state. So we can say that omega is pure if you can't find, you know, C1 omega 1 plus C2 omega 2 that's such that omega 1 and omega 2 are states and C1 and C2 are not zero. Yeah. So that generalized, and you can define that's a yeah. Then you can talk about purity in that fashion, and it's not of course this is not trivial to verify, especially because the condition of positivity is it's non-linear. Right? You have to verify that a state is positive for all algebra elements of the form, and then A star A. So that is yeah. So that introduces some level of difficulty of verifying it, but we can also use that mu inequality as as a criterion for that. And the final comment that so that's purity. And can we still talk about densities? Density? No, not well, we certainly cannot talk about density matrices, but can we talk about thermostates? And that notion is, well, I mean, if you're here, I think most of you are here just from the previous mini course, and then you know the answer is yes. There is another notion that you can talk about. It's a Kubo-Martin-Schwinger, or just KMS condition that has to do with it's inspired by um, what happens to the thermal green functions if you do have density matrices, but you can generalize. So if time evolve um, one of A, B, then you flip the order and put an imaginary power component to the time that will preserve those expectation values. So, I'm not going to discuss that in any length, but I just wanted to mention that there is the notions of purity and thermality, so to speak, are well described in the algebraic framework, even though our examples were easier because we in those example we that example we could talk about density matrix. Anyway, so now on to where we left off last time, and yeah, so there was a little bit of pedagogical decisions of how to carry on the Hamiltonian diagonalization today, and then one thing that I decided I would never skip is um, a familiar example, or an example even in traditional quantum mechanics in which you can understand why even we call it a Hamiltonian diagonalization in the first place, the procedure. If you just look at the procedure as described by Chmielowski's paper, that the one that he recommended, it might even seem obscure why we call it as Hamiltonian diagonalization. What are we diagonalizing in the first place? And if you look at a finite dimensional example, it will become clear. And and of course, the motivation from that comes in various sources. And so I'm not going to discuss at length about the construction of quantum field theory in stationary spacetimes, but at least let's see some of the obstructions. And if you use the usual, of course, we have more powerful technology now that that have developed in the past 2 days. But if you didn't have that, and you know quantum field theory in flat space, and you have wonderful properties like the Poisson-Ray invariance and the Fourier transform. The Fourier transform is a big one because that's how we all selected without even knowing. We all had this. Well, there's a natural modes. We can find a set of solutions that look like exponentials and so on. And then we can talk about frequencies. And so if you try to generalize that to a stationary space-time, and it's globally hyperbolic, it's all globally hyperbolic. And in fact, you need a little bit more than global hyperbolicity. You need Cauchy surfaces that don't approach a null part in any part. That's one of the properties you need. And also, you should also be talking about massive fields because that helps the positivity. But you could think of a product that you would promote to our mu product, that bilinear form, inspired by the stress energy tensor. In specifically, if you look at this object, which is classical energy momentum tensor for the field, but this is quadratic in the field. So you think of that as taking two arguments. If it's the classical stress energy tensor, this happens when you make these two arguments identical. I could be a little bit more concrete. I could say that A will be U and V is A U B V. So minus 1/2 of G and V C of U C of V plus M squared. Or UV. So something like that. So what you can do here, you can contract. So you're in a stationary space-time, so you can do it. You can contract this with the timeline Killing field that you have, and you integrate this on a Cauchy surface. And that, if your field is massive and your Cauchy surface has that properties that I said that I mentioned before. And again, if you want to see the details, I recommend Bernard's case 1978 paper. But if you have that, you can verify that this becomes an inner product. But so it's all the axioms of the linear product are preserved. And then of course, what you need to do is to make sure that this satisfies the mu inequality, which is non-trivial. Well, it involves some rescaling. And you can even anticipate why you need some rescaling, because you can see that if you go through this construction, also, by the way, that's a very important property as well. In stationary space-times, this is a conserved current, meaning that if this is divergence free, and this is it satisfies the Killing equation. So the object, the contraction of TAB psi A or psi B, whatever, is divergence free. So from Stokes' theorem, you know that this inner product here happens to be conserved between Cauchy surfaces as long as the fields, as long as you have nice decay properties and infinity. And the same property of independence of the Cauchy surface is verified already by the symplectic product, the Klein-Gordon product that's built out from the symplectic product. And that comes directly from the equations of motion. So that conservation is not a property of our stationary space-time, but this conservation is. Of course, we want, you could get inspiration. So part of what Hamiltonian diagonalization is going to do is say, well, why not try something like that for a generic globally hyperbolic space-time in which I don't have a killing field? Of course, this is not defined, but I can still think of this as the normal to that surface, and still the linear product properties would work. So that's a natural candidate for defining our bilinear form mu. Then we need a rescaling, and that's where, again, this is more of like a guide of how to read Chmielewski at this point than a detailed discussion of how you do it. But you can look at well, if you're following the paper. If you're not, don't worry. But if you're following the paper after his equation 24, he mentions a little bit about this rescaling of this x, in our case it's psi. And you can imagine that he needs this rescaling anyway, because he needs the mu inequality to be satisfied. And you can convince yourself immediately that you need some sort of rescaling just from dimension analysis. Particularly if you promote this to a mu operation, and you define your A operator like that, from the mu inequality, A should not have any dimensions. But if you put mu from the energy momentum tensor, which contains two derivatives, this A would have the dimensions of the reciprocal of energy. So just based on dimension analysis, you know that there has to be some sort of rescaling involved. But this is all possible to be done, and that's how, so in stationary spacetimes, because of this conservation property, if you define a mu in bilinear form based on that, this type of product, you get conservation. So you know, it makes sense to talk about the vacuum, because as you evolve your space-time in time. But if you're not, then you lose the property of conservation of this inner product, but not of the sigma product. And as you might expect, then the vacuum becomes time dependent. And it's actually more dramatic than that, and I'll come back to that a little later. That's why. But okay, so let's see what this procedure is, again from a concrete example, and then So let's look again at our in a particle. Maybe let's now consider a little more general system, but still finite dimensional, in the same spirit that we had a worked out example yesterday. And we can still, if you want to be even more concrete, it's still possible to particularize this example for an harmonic oscillator. Well, maybe that would be a good exercise if you're interested, but I can even mention what you're gonna get in the end. But so let's consider again ordinary quantum mechanics, and there is a notion of Hamiltonian diagonalization there as well. And but let's cast that notion in our language. So let's consider Hamiltonian of the form. So let me write as 1/2 of sum of Ij. And then we can write as a Mij, Ij plus Nij, Qi, Qj. And here, here I have cross terms, but I'll keep them symmetric. So I'm write as Rij, Ui, Qj plus Pj, Qy. So it's convenient if you think of phi and psi in phase space. So it's convenient to write this as simply as 1/2 of psi of phi transpose m phi, and m is this matrix, and specifically this matrix, this block becomes nr rm, ordering like that. And of course, we have our symplectic form, as we did yesterday. Well, here we may have more than one one dimension, but still our symplectic form would be sine phi. It's going to be phi transposed omega psi, and as before, our omega is 0 minus 1, 1, 0. So now let's again. There's nothing here is new, and that's how even I motivated in the first day in our review of symplectic phase space and symplectic forms. That's how it made sense. That's how we motivated that. So if you write Hamilton's equations, call that these are q dot is dh dp and q dot is minus dh dq. In this language, it becomes phi dot becomes the inverse of so is inverse of omega n times phi. Let's give this object a name. How about L? So these are the canonical equations written in one line in this matrix notation. So now there is a very natural, if these are the canonical equations, there is a very natural eigenvalue problem that we might look at now. So what happens? We want to find phi so that L acts like I omega. Right? So if you find a bunch of y's, so that Ly's omega is I omega y omega, that's pretty nice. In our quantum field theory example, this is a step that we take very naturally in stationary space spines, again inspired by Fourier transforms, because we can choose modes. There we could choose modes. Well, let me call phi omega, for which if you take the linear derivative with respect to the Killing field, the stationary. I think I'm writing too small. I might not try to write a little bigger. So if you take the linear derivative, so you look for eigen functions of the linear derivative minus I omega phi omega. So this is what we look for. This is an immediate generalization of what you do in a flat space. You have time, you have Fourier transform, you have a frequency, and you're looking for positive frequency modes and so on. So you see that there is a parallel, and one's trying to do that. Of course, for stationary spacetimes, you need to define this object. You need to, you evoke Stone's theorems, and but that's a very natural thing to do. And I hope writing this way that we are diagonalizing this matrix L makes it, at least the name Hamiltonian diagonalization makes it start not being mysterious. So, okay, so let's look at how we left off. So that's what Chmielowski's idea was. So we are already given a product. So we need to give a mu product here, and then we find another mu tilde, so that you have a pure state now. So let's see how that happens. So we need to introduce, in our example, we need to introduce a mu. Our mu is going to be based just like that mu in stationary spacetimes was based on the energy, based on integrals of, this object. You can, well, it depends. This is a plus or minus depending on your metric signature. If you're Misner-Thornton-Wheeler, you have a minus sign here for this current, and then you integrate that to represent an energy. If you're like most field theorists, then you don't have this minus. But anyway. So our mu here is going to be analogous to that. So we have this Hamiltonian, So we're going to build our mu from that Hamiltonian, and our mu is going to be phi transposed m phi. Now, there is this rescaling conversation that we had that I mentioned there was something that Chmielowski had to worry about to make everything work. And well, even before that, even in stationary space times. But here it's not. Here you see that there is a reminiscent of that rescaling property in finite dimensional systems as well. So that means let's take mu and let's take mu prime as lambda times mu. You can do that if if one of these mu's satisfies the mu inequality. Well, there's no danger for us because we are in all norms are equivalent in finite dimensions in our 2n. Well, specifically, you get one norm. There is a constant, so that norm is bounded by the constant times the other norm. So these inequalities are easy to handle. And once you do that, and you introduce this a operator, if you rescale mu prime lambda a, you can if you take mu prime as lambda mu, you can take a as lambda a divided by lambda. So if you go to mu, as lambda mu, you can take a on lambda, so that this mu tilde is unchanged. So it's it's not very, so it's, change it, yeah. So yeah, this is scale invariant. And then which is good because if the construction will use mu tilde as the basis. So if this is a scale invariant, I don't have to worry about rescaling mu and not even have to worry about the dimensions problems that I mentioned before. Because again, once we get to this stage, we are good to go. Okay, so let's find L, let's find A, let's find everybody now for this exam. Yeah, I'll raise what I just wrote. It's more natural. So one has mu psi phi is phi transpose m phi, and sigma of phi psi is phi transpose m psi, which is phi transpose m a psi. Why? Because this is mu of phi a psi. So we can find A. That's what we're trying to do. So this tells us that MA is omega. So A is M minus 1 times omega. We can also write this nicely as omega minus 1 M minus 1, right? Product of matrices. And this is nice because it's just L minus 1. This is who A is in our example. So in Chmielowski's argument, this is associated with the inverse of the field. So if this is optional, but if you're looking at his paper, this is a look at his equation 26. If you're looking at his paper. Okay. Yeah. Yeah, you can check all the properties, anti-symmetries, etc. We just put of A and anyway. Now, this eigenvalue problem now becomes this eigenvalue problem becomes the eigenvalue problems of the inverse of A, L. So this happens is the same as saying that this A acting on Y omega is 1 divided by I omega Y omega. So the eigenvalue, the eigenvalues of minus A squared is omega divided omega to the minus 2. That's the eigenvalues of I squared. So this again, this reproduces my observation, earlier observations, that is A would have the dimensions, if you don't do the rescaling, the 8 will have the dimensions of the reciprocal of the energy. And that's transparent from its eigenvalues. Now, what's nice to do is that when this matrix is positive, when M is positive, you can write this Hamiltonian or the mu form equivalently in coordinates that simplify that becomes diagonal. In specifically, so yeah, so let me I need more room, so let me write it here. So when M is positive, and that's an important condition. That's when that fails, you can already anticipate that positivity of H will fail, which is equivalent to the as positivity of mu. So the whole procedure fails. So anyway, but when does that happen? You can find physically. When it fails, you may think, well, what is failing? Is it an artifact of our? Are we not? Is it failing because we are not being creative enough with our definition as mu, or is it failing for the physical, so to speak, reason? Well, as you may see, that's saying that if your Hamiltonian now has saddle points or the inverse mass squared, or its frequency, imaginary frequency for harmonic oscillator, then you can imagine that this that we are going to run into problems. Right? So yeah, there is a set of coordinates when M is positive, in which you can write a Hamiltonian is 1/2 a squared plus omega squared. And then mu tilde, and our mu tilde by psi in these coordinates is 1/2 omega k. And well, my notation became a little, well, sorry about my notation, phi k and psi q k plus 1/omega k, psi p k psi p k. P. Yeah. Well, yeah, the notation became a little convoluted. It would have been better to write 1 and 2, and then Q1, Q2, P1, P2 instead of phi psi, but Yeah, a better choice of notation would have been appreciated. And that's exactly how we did yesterday. We take mu tilde as, so then we already have that. So we have a K map. The K map will be so as before, we now have mu tilde of phi psi 3 times the real part of K phi K psi. And the imaginary part is fixed by omega. Now, again, this is then omega mu tilde is our state, is our quasi-free state. And whose G in the S vector will be annihilated by the annihilation operator, which is Q K phi line 1. And so that is the state we are talking about. And of course, then you can find a compatible complex structure, and then it becomes a little bit of a repetition of what we did yesterday. So that's the motivation. And again, if you want to, okay, maybe let's not use our time to work the harmonic oscillator, but I encourage you to particularize this even further for the harmonic oscillator. So just one coordinate, m. So just take m as omega squared. Just take m as omega 2, 0, 0, 1. Right, so and work this example for that. Maybe at least let me show you the answer for A tilde. So mu tilde, well, I'll let you do the calculations. It's a nice exercise, but let me give you the answer. So mu tilde in that example becomes 1/2 of well, it's exactly what we had last time, right? Q. Let me put I don't know, phi 1, phi 2 to simplify the notation. This becomes 1/2 of omega Q1 Q2 plus 1 over omega Q1 Q2. And then you take A tilde, this omega A. And then this A tilde will have to be minus the square of this A tilde minus the identity, which is the condition that we had for purity in the construction of one particle Hilbert space structures. Okay, so when m is positive, so one way of identifying, so we already know when Hamiltonian diagonalization fails completely, and that is the condition of positivity of m. But the fact that given this is antisymmetry of A, we already know that the eigenvalues of A comes in pair. So we will have plus or minus frequency. So that's again what is seen in QFT as well. So that is also observed in that case. Okay. So there are many ways to motivate the construction. Some of these motivations come from thinking of an interpolating space-time. So you're given a Cauchy surface and you find a way of embedding it in a different space-time, in one in which you can use your procedures like stationarity space-times and so on. From that fictitious space-time, but then you get rid of that and you import that as initial conditions for your Cauchy surface, now in the physical space-time, and you do quantum field theory from that. You can do that. That is, There is, however, this means I think most of us will prefer to do that in a way that is completely intrinsic to one space-time and without using this fictional space-time as a way of getting help from. And also it obscures, it gives you more impression of that you have more freedom than you actually do if you do that, specifically the lapse function. So let me discuss that very briefly. So that and then let's talk about limitations of the Hamiltonian generalization. Okay, so I would like to. I don't know how many of you are familiar with the ADM decomposition. So let me very briefly mention what it is, and just so it gives us to the point where we're going to use. So I'll raise the whole board now, because kind of a bit of a transition point. So for globally hyperbolic spacetimes, if you've never seen this, if you've seen this before, you'll be a little bit more patient. But if you haven't, if you have a globally hyperbolic spacetime, there is you can decompose. So there is a family of Cauchy surfaces, and you can index them. So you can always find coordinates in which your Cauchy surface is a level surface of that coordinate. So t equals constant, so to speak. So in that coordinate, then there is you can raise the index of that, so that's the curve. So this surface is dt. So the normal to this surface is dt in that coordinate that you choose. Then you can raise the index and obtain a vector. And you obtain a vector, and you decompose this vector as a part that is tangential to the surface, and a part that is orthogonal to the surface, parallel to the normal of that surface, and that you get another surface instead. So you write this as T is N and A. That's this component plus NA, and this component. So this you also have an induced metric here, HAB, which is just GAB, GAB, B. So this projects. So this has Riemannian signature on the surface as well. And these vectors, this projects. So if you have any vector, this project that vector on the surface. So this NA, if you dot that NA with NA, this is 0. And this, so this, well, anyway, that's what this picture is trying to say. So this is called the lapse function and the shift vector. So this lapse function tells you how your clock, if you keep the clock along the integral lines of t. No, sorry, not of t. Well, if you follow the normal, this gives you how your clock behaves, and this is called the shift function. We think this is kind of an intuitive name if you're writing in terms of these. And this, if you think of this the picture is not so difficult to see why. And there are some identities that are worth mentioning. For example, root of minus g becomes n root of h. So that is an identity that becomes useful. And of course, if you take the gradient of t, it has to be proportional to the normal. So you can, why? Because, both these two vectors, both left side and right hand side, are orthogonal to all vectors that are tangent to sigma. So they must be, this A has to happen. So then you can contract this with A, with N. And from that, you get that NA is minus N gradient of T. So you have some identities there. And from that, And with a little bit of patience, this is very traditional. You can, if you want to see a heuristic formula getting this expression, you can read Mies and Thornwiller, or you can just do the calculations and being completely geometric and not very hand wavy. But you can write the line element in this way, and the line element becomes for this G, and you take the inverses and so on, becomes minus. I'm using Mies and Thornwiller now. Metric signature, Hij, dxi. This is a dxi of tangent to this surface. This ni dt, dxj is mj dt. So the line element becomes written in terms of these coordinates. And you may want to and what you can do, you can write the wave equation in these coordinates. Given this, you can write the wave equation, and the way to write the wave equation is from the definition of the box operator. That's what I suggest you do. And to do that, let's just look at a couple of identities, and then I'm not going to bore you with all the calculations. This has been a common theme of our mini course, so I'm going to continue doing that. But I am at least gonna give you the road, the map of the road. So if you are interested, you can and you have the time, you can try to go ahead and do it yourself. So for example, if you contract that, so if you anti-symmetrize this object, using that identity, you can write this as radian of limestone should reading with B T plus B N A of T. And then so then we can write this as NB N minus NA long of N, and contract with N again, and then again NA FA of NB minus NA B of NA. That is NA rated of A log of N and B minus NA and A rated B of log N. So this is -1, so this is a +1. And this you can move this to the you can move this to the middle, and because NA has constant norm, namely in -1, this is 0. So you get a formula for the acceleration vector, which is the double derivative of the n vector. So we write this as AV equals NB and A radian of log n plus radian B of log n. And now you compare that with given HAB, you can find the corresponding covariant derivatives on sigma. So I'm calling them capital D. So capital D is the connection that you get from sigma itself. So you can compare this formula with this log. So to get that from, if you have a connection on the whole space-time, and if you're going to put that, all you have to do is project every vector to to sigma and the derivative to sigma, and this will induce you with this capital D derivative. So dB of log of n becomes HBC, right? C of log of n. We can write as delta CB plus NB and C, gradient C log of n. So, and this is similar to that. So the conclusion, if you compare these two, the conclusion is AA is dA of log of n. So that's an identity that I wanted to mention. And what you want to do now, we're going to want to write wave equation in terms of the Laplace Beltrami operator on sigma. Why? Because again, if we write that way, we can identify the elliptic operator when you separate the wave equation into the part. Okay, let me just do it. So the Laplace Beltrami operator on H of a function U will be HAB number A of HBC number C of U. And this is, oh dear. Okay, well, let me just do it very quickly. This is HAB number A number B U plus HAB number C U number A HBC. And then you write this is nabla, like this is nabla A with delta BC plus NB and C. So this is so if you put this together, you get this is HAB U, and this term is in the box operator for the space-time box operator. So this term is the term that we absolutely want to keep. Plus HAB, CU, and C H of H. The what? Well, anyway, let me skip some steps. Plus K and C U. And this K is a trace of the extrinsic curvature, or the second fundamental form, however you want to call it, of the surface. So the reason I'm doing this is now that we can write this box operator U. Yes, as well. Let me use the metric. The metric is minus A and B plus HAB. This is the inverse metric. Number A, number B of U. So that's the box operator, but this becomes written in terms of these functions minus and U. So second normal derivative of U plus the acceleration vector, which you can write as that way. So let me even write. So this will be AI, AB, gradient B of U. And this is ugly, but it's not so ugly because of this property. So you can write this as D, capital D, I, or log of n, di of U. So now everything is intrinsic minus K and N, K, N of U. That's the box operator. Now it's in this ADN form. You can find this in literature. It's very rare to find someone, calculating this. But the Laplacian on U. So if we think of of a particular surface. This is not the conditions that you will find in the papers that I'm mentioning, but one way of simplifying everything is if you have this minimal surface. So in other words, if you choose a surface in which the extrinsic curvature has trace 0, this term disappears, and this becomes what we want to, if I wish we had Fourier transforms, so this is the term that wishes we had Fourier transforms, and then we can write the operator as such. So this term, let me write this term. So this n of u is u plus vi log of n, vi mu, using the wave equation, minus box m u, mu is the mass. And then it's nice because I can write this as 1 divided by n root of h di n root of h hij dj of u minus mu squared. Recall that there is this lapse function. Okay, so this, now the integration measure, when we're going to integrate that on a surface, we are going to integrate that on root or n. So the measure that we're looking now is this. I have another 1 over n here. So that would be the natural, just like the induced, the box of the part of the operator that is a Laplacian in the induced surface, except that there you have this mismatch between what you integrate and the natural L2 measure from this operator. So inspired by that, we have to remove that. So what we can do, we can define P, the P operator, as minus 1 over root of h without the n, di, and root of h, hij, dj, plus n times mu squared. So I multiply by n. And then from that, so then this object now is symmetric and positive in this integration measure. Without the n. Sorry, in this integration measure. And that's consequential. Because now we can define a product. Now we can define a product which is, u p of v given by that expression, and then you verify that p is now symmetric, and because n is bounded from below, you have a natural inner product. From that, we can define a mu. Now we can define a mu function, which I define as the integral over sigma phi 0 u complex conjugate. Because this is positive, I can take the square root of this object. All right, phi 0 u plus pi u 0 complex conjugate. Well, this is complex extension already. I'm extending this to complex numbers. Now, this solves everything you want to do. And by using these constructions in P and putting the P's into the 1/2 and P to the 1/2 minus 1/2, you can also verify that this satisfies the mu inequality. And the way to do that, you can just insert, from sigma uv was integral of sigma of phi 0 u phi 0 v minus phi 0 v phi 0 u root of h to 3x. Now you can insert p to the 1/4 minus 1/4 times p to 1/4 in that definition, and integrate by parts, and you verify that this is satisfying mu inequality. And then furthermore, you need and you see how this acts on the pair with phi pi. So you're seeing now it is initial data. And so that gives you initial data. See, in other words, if you choose your phi as you please, you choose your phi as you please on your surface sigma, then you choose pi. So the procedure is you choose phi as you please, and then your pi, you have any freedom, all the freedom in the world to choose your initial conditional sigma, and as long as you fix your pi as this. If you do that, you are given, by construction, your A will be acting trivially. In other words, you declare this mode as one of your mode solutions. Of course, now there are many comments in order here in this construction. First of all, this is all very elegant. So this maps your freedom in choosing your initial conditions as if you choose a specifying condition. That this explains the construction using that auxiliary spacetime idea, because this is the derivative that you would obtain in the fictitious spacetime. So in that fictitious spacetime, you choose my initial modes using the fictitious spacetime. The fictitious spacetime now has this extra n here. And that is the reason why, if you're using that fictitious spacetime, you not only choose it to be not only do you choose it to be static, not stationary, but you choose it to be ultra static. So you make the lapse function constant everywhere, and that is mapped so that this P has the properties that we need in this construction. So this shows you that you are not free to choose your lapse function in that auxiliary spacetime. But there you go. Of course, in practice, so this is all elegant, but in practice, how do you take this P? Like, I'm writing this very casually. These are well defined because this is positive, and then symmetric. You can check symmetry by integration by parts as usual. But how do you do this, right? So how do you calculate explicitly this object? Well, this is kind of taking the square root of minus the Laplacian plus mu squared, and it's not easy to do that in explicit calculations. What you do, you take this spectral you calculate it from the spectral theorem, but that means solving the wave equation. So there is no miracle here. If you want to do a specific, if you want to actually perform the calculations, there is no miracle there. But at least it has the advantage of No, in flat spaces, it's just P is just minus Laplacian plus mu squared, right? But in it's in not if not, it's something even more complicated. So yeah, so now you wanna still has to calculate that, and then so yeah, it's not easy. But there are some examples that in which you can you apply this procedure and be happy about. Now, the Hamiltonian diagonalization has its severe limitations. First of all, it's not always applicable, as I mentioned. Another severe limitation of that is the fact that vacua now is time dependent. You can only choose your vacuum at a certain time. And it's even more dramatic than that. And if you go to our, one of our references in our syllabus is the PhD thesis by Wolfgang Juncker, 1995. So if you look at that, section 5, if I'm not mistaken, he shows something even more, even more concerning about the Hamiltonian diagonalization. Because at this point, it's a complete open question if I do that, can I still talk about energy momentum tensor? And that's why I mentioned very briefly this in our second day on Tuesday. I mentioned that surely we are talking about this algebra that's nice, but some what we want to call observables in quantum field theory might include products of phi's in ways that you need to take the coincident point, coincidence limit, etc., and that is non-trivial. Not all states will allow you to know that they, if you already know how, well, you need to regularize. What I'm saying is that you need to regularize your state to obtain finite like, answers. And if you know how the UV behavior works from, for example, flat space, you can remove that divergent behavior from it. And what you get in the end is something finite. So states in which there are states that are singular in a way that is in the way that is expected are states what we call Hadamard. And there is more than one equivalent way of characterizing Hadamard states. One is by looking at the 2-point function in the UV limit. That's Hadamard parametrics, and as you can also look at micro-local characterization. Then you look at where the singularities are and where they propagate, and so that's another way. But in any way, you need a further condition and a further restriction in these states, so they can be called physical. Can you regularize them? So, and with all the freedom we have, like we have the freedom choosing compactly supported functions phi. And once you do have, you can call it. I remember what I wanted to say. The reason I said I was mentioning that it was so difficult to calculate this explicitly, you needed to invoke spectral theorem, etc. That should ring you a bell, because if you look at traditional expositions of quantum field theory, they're not algebraic and etc. You're always tied to that. They don't use this language, but you are tied to that one particle Hilbert space structure. And so you can only use functions that are there. So you're not free to use any complex solution. So if you want to construct a one that is physically acceptable, you need to make sure that it's not only it's positively normed, but it's made of only of purely positive normed functions. So that's what this helps you to do, at least symbolically. Of course, in practice, it's about the same level of difficulty, but that's what this is doing. That's the remark I wanted to make. I'm sorry for the confusion. But back to Wolfgang Juncker. So what he showed is that he gave a concrete example in FRW, in physical Robinson-Walker spacetimes, with k equals 1. He constructed an example in which the Hamiltonian diagonalization, he could show that the vacuum obtained that way, not in this language, but in the language of Chmielowski, is not Hadamard. So this situation is not guaranteed to produce you any physically acceptable states. And actually it's known that at least in a particular case, it does not work in the sense of producing physically renormalizable states. His construction is not so, his proof is not, there's a theorem relating what happens if you have compact Cauchy surfaces and unitarily equivalence. There is a result in that if you have the Hadamard condition. So what he verified is that his concrete construction, you don't have that property. Consequently, your state couldn't have been Hadamard. So maybe for that reason, Hamiltonian diagonalization is not as popular as once it was, especially in the times of Ashtekar and others. But I still think that this is a lot. It's instructive if for any other reason to apply our constructions of one particle Hilbert space structures in that way. Okay, let me ask you if there are any questions, and there's something fun that I want to do now. Are there any questions? What I want to do now is I prepared 12 questions, multiple choice. I'm going to share them with you, all anonymous. So there is no, there is nothing that you should, there is nobody going to be fear of getting exposed or anything like that. It's all anonymous. It's meant to be fun. The questions, to answer these questions, you don't need to do any calculation or think for a long time. So they are meant to be, you read, you think for a few seconds, and you choose your option. So I prepared them. So what I want to do now, I want to share the link to the Google Forms with you. So this was originally intended to be done using polls on Zoom. I know that if you are in the webinar mode, this is easy to do. But in the testing, we had the Zoom room a few days before this mini course started, and I tried to test the feature and I couldn't make it work. So they said, well, okay, you know what? Let's use Google Forms because I have control of Google Forms. And I'm going to share the link with you. So what I'm going to do is, I'm going to share the link with you, obviously. And let's read the questions together, because if the questions are, if there are any possibility of interpreting these questions in more than one way, we can read it with you, and also for the YouTube. So for people who are watching us on YouTube later, they will know what we are talking about, and then we can see the aggregate results, see how everyone done overall. You can keep track. And then share and I'll share the right answers in the end, and you can see how aggregate. So as a group, how we done, and you can also see yourself. Let's see, even if all of that you've never seen any of that before, I'm sure you're still gonna get some questions correctly, and then you see how many of that you got correctly. How does that sound? Can we try that? And that's also, so let me share the link immediately, and I'm gonna share in the chat. There you go. So let's read the questions together. So if you please fill it out. Again, it's all anonymous. So there is absolutely no embarrassment. So let's read the questions together. So Clara is here. Great. So if there is any technological issues, please, Clara will be here to give us some help. So the first question is, the bilinear form sigma that defines a dynamical system, S and sigma, is required to be? Now you have a few options: symmetric, positive, definite, antisymmetric and non-degenerate, symmetric and non-degenerate, antisymmetric and positive definite. So make your choice. Okay. Second question. Please, if anyone is having technological issues, please let me know either by unmuting yourself or writing in the chat. Clara is here to help as well, so we can sort it out. Let's go for question 2. A quasi-free state, which is also called Gaussian state, omega mu, so mu is completely determined by its one-point function alone, the choice of the algebra, the Weyl algebra alone, all of its endpoint functions, which are logically independent, or its two-point function. It's a quasi-free state. So what do you think the right answer is? Just make your selection. All right. So next question, third question. The inequality, the mu inequality. So the magnitude of sigma psi phi is bounded by mu phi phi to the 1 half, square root of that, square root of mu psi psi. So this condition exactly guarantees that omega mu, the omega that is built from that mu, so the exponential of 1/4 of mu f phi mu mu divided by that by equal 4, is that pure state? Is the omega mu is pure state? That's the first option. The second option is that mu defines a state. In other words, that omega mu is positive, which is one of the axioms of a state. That mu is a KMS state, omega mu is a KMS state, so that a thermal state in algebraic framework, or omega mu is Hadamard, so it's physically acceptable in the sense that it's renormalizable. So what do you think it is? All right, next question. Quasi-free state is pure if and only if the Cauchy-Schwarz bound is saturated. That Cauchy-Schwarz is the same one that we had in the previous question. With A defined by sigma of phi psi is mu of phi A psi, and the polar part of A, what is purity equivalent to? So is a magnitude of A 0, 1, A itself is 0, or is mu equals to sigma? Selection. Our next question, in the one particle Hilbert space structure, Hilbert space, complex Hilbert space H, and a K map of a quasi-free state, the map K from S to H is real linear, and Ks plus IKS is dense in H, complex linear, unitary isomorphism from S to H, or the identity map. Make your selection. Next question. In the tilde vacuum, one has 0 tilde, A dagger A, 0 tilde, so that number operator equals to magnitude of beta squared. So a non-zero beta means what? That the two vacua are the same state, that the two vacua are not in the same folium, that the modes Q mu fail to be orthonormal, or that the vacuum differ, but they may be in the same folium. And make your selection. Now, next question. A Bogoliubov transformation A tilde alpha A minus beta A dagger preserves the commutator A dagger equals 1 if the A tildes with the tildes is the same as without the tilde. So what does that entail for the coefficients A and alpha and beta? Now there is just one mode, so there's just one coefficient alpha and one coefficient beta. Does that mean that alpha is the same as beta? The square magnitude, the sum of the square magnitudes is 1. The difference of square magnitudes is 1, or beta is 0. Your selection. The next question, when does this Hamiltonian diagonalization fail? When there is more than 1 degree of freedom, when the Hamiltonian is time dependent, one may have infinite particle productions at finite times, when Hamiltonian is positive definite, or then the eigenfrequencies of omega become imaginary or complex, or which means in unstable and inverted modes. We're going to discuss all of that after, when we see the results. And then, so, see. Right. Next question. Two commuting time-like killing fields X and Y give equal Ashtekar Maganon K vacua. That is, well, that's introducing this terminology now, but this is what we've discussed today, the construction of based on stationary or static stationaries, or just globally hyperbolic spacetimes. Ashtekar Magnum for the former, and the so their KMS thermostates did not agree. What's the reason? Is the algebra strictly included one in the other? The KMS states are not in the same volume. Purity fails in one of the two states. Or X and Y generate different time evolutions. Next question. The one particle structure fixes two inner product K phi 1, K phi 2, mu phi 1, phi 2 plus I sigma phi 1, phi 2. With this convention, positivity of mu is mu 1, mu 2. Well, again, that the square of sigma, if sigma squared, the mu, what I've been calling the mu inequality, is an extra axiom unrelated to H, equivalent to purity, the Cauchy-Schwarz inequality for the inner product in H after the projections in K, or the KMS condition. All right, next question is related to our yesterday, so the construction, the explicit construction that we had yesterday. You don't, even if you missed yesterday's class, this is still you can think of that as a question about standard subspaces. So consider the set of all W in C's. For all W's in C's, you consider the pair cosh of theta times W and sinh theta times the complex conjugate of W is a proper standard subspace. What happens in the limit? Beta goes to infinity, so that you have to remember what theta is. So when beta goes to infinity, that was the case of cosh going to 1. So options are H stays as proper standard subspace, meaning that dimension, the real dimension is smaller than the complex dimension of C squared, the real dimension of C squared. H goes to C direct sum with the null, with the zero vector, becomes a complex subspace in the mode decouples and states become pure. H fills all of C squared, or H collapses the null to the zero vector. Make your selection. And final question. A quasi-free state is pure if its one particle subspace KV satisfies what? K V plus IKV is dense in H. KV alone is dense in H. The intersection of KV and IKV is the zero vector, or KV is a proper standard subspace. All right, these are the 12 questions that I had. Let's wait until the answers come in, and let's share them. All right, the answers are still coming in, so let me give you a minute. All right. We don't have many responses yet. So if you just want to power through, I'll give you another minute. If you haven't filled in the form, you want to power through it, feel free to do it. So we have a little bit more statistics, and it's going to be more interesting to see what they look like. Can you visualize? Actually, let me ask you this. Can you see the aggregate responses once you finish filling out, or is it invisible? All right. One more minute. No, okay. All right. So I'll share my screen in a second. Let me give you one more minute. Huh, I'm glad you like it. I'm glad you like it. We want to make this a little bit more interactive, and every I know Ricardo tried something related to getting people to share why they were interested in Tomita Takizaki, and I'm trying this instead. Um, all right. Very good. Shall we? Okay, let's do it now. Let me share my screen. And it's going to be new to me as well. I have no idea how the distributions are going to look like of the answers. So this is going to be a surprise for me as well. So can you see my screen? Very good. So let's look at the responses. The bilinear form sigma defines a dynamical system. Yes, all right. Okay, most of you got it right. So over half of you got it right. It's required to be antisymmetric and non-degenerate. And again, as a refresher, why? That's related to the fact that well, antisymmetric has to do with this minus sign in Hamilton's equations, and non-degenerate, we need to take the inverse of that, right? We need to take the inverse we wrote today, and we write the equations of motion as that inverse omega to the minus 1 times m. So if that as a matrix, that omega is singular, there is no hope of rewriting it with Hamilton's equation. The system is not Hamiltonian. It's not classical mechanics as we know it. Right? So that's most of you got it right. Very good. Question 2, a quasi-free state. Yes, very excellent. Most of you got it right. Very good. So it's right, excellent. So I think the second favorite question is all of its endpoint functions, which they sympathize with the answer. After all, you may think that, but again, if you studied even in flat space, Wick's theorem, you can relate endpoint functions to the 2-point function. So the physical content of your state is in the 2-point function and for quasi-free states. And that is why that mu was so important. Well, I mean, that's why it's maybe a loaded way of phrasing it. But yeah, so that's one of the reasons why we are worried about specifying the 2-point function so much. Okay, the inequality is exactly the condition that, yes, again, most of you got it right. It's the condition that it is a state. Without that condition, we don't have, mu doesn't define a state. The positivity of omega sub mu is not guaranteed, and it's not a state. The second favorite condition was a pure state, which again is sympathized. That is related to the saturation that we discussed a lot yesterday, but this is an inequality. So as an inequality, it just defines a state at all. All right. Okay. Next question. Yeah, so you're doing well. We're doing well collectively. There we go. That's correct. So a quasi-free state is pure if and only if it's saturated, and the conditions in terms of A, magnitude of A is exactly what you said. Magnitude of A is one. Very good. One and dimensionless. That relates to the discussion when we had today. Very good. Very good. In the one particle Hilbert space structure, oh, this we have there's a little bit of more division of the responses of a quasi-free state. The K map is yes, correct. Most of you got it right. Yes. Yeah, it's real linear, meaning that you can multiply by real numbers, and then you have linearity that way. And dense, and that's again, this is to replicate the density condition is to replicate what you do in flat space when you say that you get A times the mode plus A dagger times the complex conjugate to that mode. So that's that's what it can, that's the condition remains once we go to generic one particle Hilbert space structures. Yeah, there is no there is no isomorph. There is no there is certainly no condition of unitarity in isomorphism here. Yeah, so we have an observation here in the chat. Strictly speaking, a quasi-free state can have non-zero mean. Yes, which means that the zero. Correct. Yes, correct. Very good. Yeah, that's. I'm glad someone pointed that out. Yes, so the 1 point function, I'm not saying anything in this case, and so an even better response would be to include that in the 2 point function. So what you do, you can to define in the algebraic framework, if you want to talk about a coherent state. Well, so Pedro says we do have though the freedom to shift the field operator by a C number so that yes, right, yeah, spot on, yeah, excellent. Thanks for that observation. I think this is very instructive. What you do, you can find a real solution if you have any if you have a state and of the vacuum and you want to build a coherent state on top of that vacuum, what you have to do is just find a real solution and you build the 2 point function of it as the product of those solutions. Yeah, that's correct. So strictly speaking, maybe people wouldn't call that states a vacuum, but I did leave that option open. But in any case, I think from the options that we had here is from the options that we had here, the better choice would be the ones that most people got anyway. But thanks for that observation. It's very correct. Yeah. Okay. Yeah, we talked about this one. Let's see this tilde vacuum. I'm glad you got this right. Very good. So most of you got right. So a non-zero. So yeah. So well, I'm okay. I'm slightly surprised by this distribution of answers in this question. I expected more red choices, not as many blue choices. Well, the correct is green. So you got this right. The correct is green, so it just means that you have mixing. So some of your modes that were annihilated, now you need creation and annihilation operator to build them, so that they are not the same state, but the condition of being unitarily inequivalent has to do with something else, which is that the condition of having a trace of beta dagger beta finite. So that is a stricter requirement to have than that. Now, yeah, so I think that addresses the blue answer, and I thought more people would select green based on previous interactions with people. No, not people who took this mini course. So I guess if the sample sizes were big enough. I think this is good news. That things that someone got this right. Now the Bogoliubov transformation. Yes, most of you got it right. And again, that's that. And then I wanted to observe that this is like cosh squared minus sinh squared equals 1. So that is related to the fact that we chose. That's one of the reasons why I chose cosh, introduced the theta variable yesterday, so that this Bogoliubov transformation, this condition of Bogoliubov transformation becomes um, uh, natural, and it becomes an identity for any theta. And then and that's also related to why that example that we worked out in detail yesterday is not so silly. In fact, that if you write even the Unruh effect, I had it. Yeah, so if you write the Unruh effect in modes and you split in left moving modes and right moving modes, you get something very similar to the construction of the one particle to that standard subspace that we worked for the thermostat yesterday. It looks very similar. So again, so if you're comfortable with that, and if you want to decompose the left movers and the right movers um, in 1+1 Unruh state, you're gonna see that the calculations are strikingly similar. So anyway, very good. Okay. Yeah, that's what we did. I don't know why I scrolled up. The standard Hamiltonian diagonalization construction fails when. So most people most people chose, yeah, most people are thinking that it's when Hamiltonian is time dependent. Yeah, so that is a problem of the Hamiltonian diagonalization. That's okay. I would say that the red answer is an undesirable feature of the Hamiltonian diagonalization when the Hamiltonian time dependent. However, you can still do it. You can technically speaking, you can still define a time dependent vacuum that is only good for a certain Cauchy surface, and then you don't have don't have stationarity. So certainly things are going to change in time, and so that's no surprise from that. But it's again, you lose this property that you would have in stationary space times. The correct answer is green, which is the second favorite. When the eigenfrequencies become imaginary, which is equivalent to saying that the matrix M is negative. In that case, you cannot define states in any way. So it's a much more dramatic effect in that way. So that's a little bit of a tricky question. Some people selected. Oh well, I guess. Yeah, I guess this is not a very well formulated. I give you orange people as well. Yeah, I should have been more careful when I wrote the options here. Yeah. Yeah. All right. So orange people, good. All right. That's another the kind of wow, that's a bit all over the place. Yeah, that's a bit difficult, but that's a bit difficult. And to be fair, we didn't discuss that at length, so I take the blame for this division. But the correct answer is green. X and Y generate different time evolution. So the KMS condition is tied to a time evolution, and different time evolutions will give you different KMS conditions. Now, a very popular answer is yellow or orange, depending. It fails one of the states. Yeah, in fact, purity will thermostates will not be pure in general, so that will not help you that much. Yeah, that was a tricky question, but again, this is I'm not surprised that responses are divided like this because we didn't have time to talk too much about it. All right. You want particle structure fixes? Yeah, excellent. Yes, yes. Very good. So this works as this is to say, wait, where did it go? Okay, here. Yeah, that is to say, where did it go? Oh, here it is. Yeah, that is to say that, yeah, so once you have your one particle filter, you succeeded in your particle Hilbert space structure. You are only interested in vectors after they are projected by the K map. And then in that, you just have the Cauchy-Schwarz inequality. That's exactly what it is. And that, good. So in H, that's the Cauchy-Schwarz inequality. All right. From yesterday, so we have this one for the thermal one mode state, proper standard subspace. Yes, half of you, exactly half of you got it right. So what happens is, more than half now. What happens is that you have the second entry in the direct sum, the sum that if you think of it, the thermal field double, so that part that purifies the state, you're just a null vector in that case. There's nothing there. It's all that you don't even need. The state is already pure in the Hilbert space. You don't need to purify it by doubling the number of degrees of freedom, and that's exactly as manifested in making that projection 0 from the second entry in the direct sum. Yeah, so there is some popular. Yeah, so that the exact opposite of that is blue, and then and H feels, yeah, all right. Okay, final question. A quasi-free state is pure if the one particle Hilbert's pressure satisfies. Yes, most of you got it right. Yes, the alone, KV alone is dense in H. So in that case, we can also say that it's complex stable. Yeah, IKV is you bring it back to that to KV, and that is a little bit of a KV is dense in H. So that's the condition of cyclic condition, which is or standard subspace. A proper subspace is the opposite of that again. All right, that's it. That was our nice. How did you do? I mean, did you get? Now you can check yourself how many you got right. There's no way I know, but you can count yourself how many you got right, and then hopefully this will see that you got some of the core ideas you may have taken with you. If you're interested in as an exercise, I would also encourage you to revisit the Unruh effect derivation. Perhaps you can even, if I had, maybe 40 minutes, I would even do that just to go full cycle. You just look at a simple case of a two-dimensional case, and then you have a pure separation of left movers and in movers, cast the Bogoliubov transformations for the right and from the left, and then you have the condition alpha squared minus beta squared equals 1, and write the proper standard subspace in a way that is going to look a lot similar to the discussion that we did yesterday. That will be very nice. I will continue to check. Well, okay. Are there any questions here now, or maybe about this questionnaire? If I'll give you some time for people to type. As you type, let me say a few more remarks, and specifically that I will check our Slack from our grasp for a few days. If after a few days I'll stop checking, but you can still reach out to me. You can email me. My email is bcosta@troy.edu. Maybe let me try. We can email me if you want to talk, and if you have something that we'd like to discuss. If you're an undergrad and if you're interested in and pursuing a master's degree in mathematical physics, that keep an eye. We can work together maybe. Anyway, so yeah, so I don't see any questions, so I think that's it. We'll finish here, and please join us tomorrow, which I'm hoping it's going to be a fun day as well. Let's have conversation. Carol is also going to be with us talking about the wheat detectives. Well, we all three of them are related to the event next week, and yeah, I hope it's fun. And bring questions. I mean, this is going to be it's going to be fun as if we have a lot more to discuss about. So I'm signing off now. Thank you very much for attending, and I hope you have a great day. Cheers.
Hi, Bruno. Also, saying to the people that tomorrow we have the round tables of careers and opportunities. You are all welcome to participate. We have two in English and in Portuguese. Yes, I think it's a good opportunity to you guys.
All right, stop the recording now.